So this is Jeff Hamrick at Rhodes College again with a brief discussion about how you use the student t-distribution calculator that we built for you using Mathematica. This is a Mathematica notebook that we've opened up. It's the t_distribution.nb file. You can download it from our central Moodle page for the course. If you left click, in this cell so that your cursor is blinking in that cell, and you press Shift Enter, and answer this question by pressing enter again, answer the question yes, then Mathematica will generate a student t-distribution calculator for you. It looks quite similar to, and in fact in most respects is like the normal distribution calculator, except that the normal distribution depends on two parameters, a mean mu and a standard deviation that we usually call S or sigma, depending on the context. The student t-distribution, in contrast, depends on only one parameter, the degrees of freedom, which is denoted up here by df. Okay? So if you change the degrees of freedom from, let's say, 10 to 25, you'll see that the shape of this distribution does not really change all that much. If you change it from 25 down to something like 3, the change is a little bit more extreme, but it's still not all that dramatic. The student t-distributions, as you'll recall from class, converge as the number of degrees of freedom tends to infinity to a standard normal distribution, and they do so relatively quickly. After about 75 degrees of freedom, a student t-distribution is hard to differentiate from a Gaussian distribution, a standard normal distribution. Okay, so there are two things we can do with this probability calculator. We can compute probabilities and thresholds. So let's ask ourselves two or three questions and answer them. Suppose that we have a student t-distribution with 8 degrees of freedom, and we'd like to know the probability that a random quantity from such a distribution is less than 1.2. What would we do? Well, change the degrees of freedom to 8, and then change the critical value to 1.2. And we see here in this statement that Mathematica is doing the computation for us that we've asked for. The probability that a random quantity x that has a student t-distribution is less than 1.2 is about 86.777%. Okay? If we want to ask ourselves the question instead, what's the probability that a student t-distribution with 7 degrees of freedom is greater than the value 2.3, what would we do instead? Well, we'd change this to 7, change the critical value to 2.3, but now to sweep out the right tail probability, we would change the area choice here from left to right, okay? And read the statement again with me. The probability that x, a student t-distribution with 7 degrees of freedom, is greater than 2.3 is equal to 0.02750, or about 2.75%. Okay? We can also ask the inverse question about critical values or thresholds. What is the threshold, for example, such that 30% of the probability underneath the student t density is 30%, let's say? So change to critical value. It wants a probability between 0 and 1. If we're still going to use the same student t-distribution with 7 degrees of freedom, we type in 30% probability here, and I'm going to change the option back to left, and we get this. Okay? So the threshold such that the probability that a student t random quantity is being less than that threshold is equal to 30%, that threshold is minus 0.54911. Okay, one more example. Suppose that we have a student t-distribution with 20 degrees of freedom. What is the threshold such that 42% of the probability mass underneath the curve is greater than that threshold? Well, I'm going to change the degrees of freedom to 20, change the probability value to 42%, and change the area option to right. So we see that 0.204538 is the threshold such that the probability of being above that threshold, if you're working with a student t random quantity with 20 degrees of freedom, is 42%.